Good everyone, my name is Graphics. If you look at the front of the screen, you are going to see a circuit, and this circuit you're seeing has 4 mesh, right? And it has 7 elements. In each element, we have both the passive and the active. We know, like I said in my earlier video, the active element are the one that produces current in the circuit, right? And we have one of the active element, which is the independent current source that has 10 ampere, and we have the 2 other active element, which is what? The independent voltage source, which is the 5 volts and the 10 volts source. And we have 5 resistance, which are the resistance that has the resistor, 5 resistors, which are the resistor with resistance of 1 ohm, 2 ohm, 3 ohm, 3 ohm, and 2 ohm, respectively. Now we are told to use super node technique, or we say super node analysis, or super node voltage method to analyze these circuits. Is that taken? And if you look closely, right, the first thing you do for me to enhance your understanding is that I'm going to label this circuit round. So I'll say here should be my A, B, C, D, E, F, G, H, I, and J, right? Now, for we to start, we need to look for the best node to take as our reference point. And there are 3 of them here. We have the node B, node C, and what? Node D. Now, why am I taking this node? The reason I'm taking this node because of what? This node is 3 branch are attached to this node, right? So there is just a junction where 3 branch are attached to, because from B you can go to C, from B you can go to I, from B you can go to A. Similarly, from C you can go to B, from C you can go to D, from C you can go to H. Similarly, from D you can go to E, from D you can go to D, from D you can go to G. So you see we have 3 different branches attached to this particular node. So the 3 node that is qualified for we to select is B, C, D. Now on those node, I will take the first node to have a voltage, right, of V sub 1, that is V1. Then the second node, which is node C, I will take it to have a voltage of what? Of V2. And the third node, which is node D, I'll take it to have a voltage of what? Of V3. Are we together? Now let's start. Consider node B. Applying Kirchhoff current law at node B. You see that what does the law says? It says that the current entering the node is equals to the current leaving the node. Now if you look at node B, what current is entering node B? The 10 ampere independent current source is moving in this manner towards node B. So we'll put it down because that's the current entering. That is the only current entering node B, equals to the current leaving. Now if you look at which current is leaving node B, you look closely, I1 is leaving and I2 is leaving. Look at the arrow. They are both moving away from node B. So and the law says the current entering equals to the current leaving. So since I1 and I2 are leaving, they are partner in crime. Are you with me now? So we are going to say I1 plus what? I2. I'll term that equation 1. But I1 is equals to the voltage from where I1 is coming from, which is what? V1, minus the voltage to where I1 is going to. Since there's no voltage, so we say the voltage is 0, and V1 minus 0 is V1, all over the resistance between them. And the resistance between them is what? The 1 ohm that we have there. and V1 over 1 will still give us what? V1. So we have V1 here. I'll term that my equation 2. Similarly, I2 is equals to the voltage from where I2 is coming from, which is V1, minus the voltage to where I2 is going to, which is V2, divided by the resistance in between them, which is the 2 ohm that we have there, right? I will term that my equation 3. Now, substituting I1 and I2 into equation 1, we're going to be having, we know equation 1 is 10 equals to I1 plus I2, right? So we're going to be having 10 equals to, so I'm writing my I1, I'll put the value of I1, which is V1, plus, so I'm writing my I2, I'll put the value of what? Of I2, which is what? V1 minus V2 all over 2. And if I simplify this further, we have 10 will now be equals to V1 plus, now the coefficient of V1 here is 1, so 1 divided by their denominator will give me what? 0.5 V1, minus the coefficient of V2 here is also 1, so 1 divided by 2 will also give me 0.5 V2. So if I collect like terms, my 10 will now be equals to 1.5 V1, because 1 V1 plus 0.5 V1 will give you 1.5 V1 minus 0.5 V2. I will term that equation 4. Please subscribe if you are finding this helpful and like the video. Thanks for watching. Now consider node C. Applying Kirchhoff current law, the KCL to node C. Now if you look at that node C, we have a current coming into node C, right, from node B. Is coming to node C. But if you look at the next part here, there's no current coming from node D to what? To node C. We only have a voltage source of 5 volts in between them. That is the main reason why we're using the super node technique. Now, what is super here? We will not take point C as our super node. Why do we take our super node? Because we assume that point D, you can look at my diagram, is now coming together with what? Point C. They are now the same point. So we assume point D to be what? Point C. So you see that I've moved my diagram here this way. So to now be what? The I5 that is coming into what? The super node C here. We make it super because of what? The point C can accommodate the point D. Is that taken? So because of I1, I2 is now coming into point C and I5 is coming to point C, we will now say the current entering is what? I2 plus what? I5 equals to what? The current leaving. If you look at it now, once you bring the node what? The node D to node C, 2 currents will be coming down. I3 and I4 will be coming down, right? So since both of them are coming, we assume that both of them are leaving point C, because C and D are now 1 point. So we're saying that what? I3 plus what? I4. We'll term that my equation 5. Is that taken now? So the current entering equals to what? The current leaving. But I3 is equals to the voltage from where I3 is coming from, right? The voltage from where I3 is coming from is V2 minus the voltage to where I3 is going to is 0, because there's no voltage there. The voltage there is 0. That is the reference, the X here. So V2 minus 0 is still V2 over the resistance in between them, which is 3. So V2 all over 3, what we have there, I'll term that my equation 6. I4 happens, the same thing happens. It's equals to the voltage from where I4 is coming from, which is V3, minus the voltage to where I4 is going to, which is 0, divided by the resistance in between them, which is 3. So we know V3 minus 0 is V3, and we have V3 all over what? Over 3 here. I'll term that my equation 7. Now, I5. I5 now is equals to the voltage from where I5 is coming from. You can look at my arrow, right? Coming this way, and we have 10 volts minus the voltage from where I5 is going to, which is what? V3. So minus V3 divided by the resistance in between them, which is 2. So we term that my equation 8. I ignore equation 3 here, equation 2 here, because I already sought for it when I was dealing with what? The node B. So I don't have to repeat it again. Now, we've gotten all what we want here. Now, you will now substitute in I3, I4, I5, and I2 into equation 5. So let's see, we know this is my equation 5, I2 plus I5, right, equals to I3 plus I4. So instead of me writing I2, I'll put the value of I2, which is V1 minus V2 all over 2, plus, instead of me writing I5, I'll put in the value of I5, which is what? 10 minus V3 all over 2, equals to, instead of me writing I3, I'll put the value of I3, which is what? V2 all over 3, plus, so when we're writing I4, I'll put the value of I4, which is what? V3 over V3 also. Now, since I have this, like I always tell you, the best approach is to do it the way I'm doing it now, instead of you looking for the LCM and so on and so forth. Now, if you look at V1 here, the constant of V1 here is 1, and is divided by 2, so we'll say 1 divided by 2, that will be 0.5 V1, minus the quotient of V2 is also 1, divided by 2, we're having 0.5 V2, plus 10 divided by 2 is 5, minus the quotient of V3, which is 1 divided by 2 is 0.5 V3, equals to the quotient of V2, which is 1 divided by 3 is 0.33 V2, plus the quotient of V3 is 1 divided by what? 3, and we have what? Still 0.33 V3. When I mean coefficient, I mean the value close to that variable. So if you look at the V2, V3, V1, they have a value close to it, and that value is what? 1. That's why I'm dividing the denominator 1 by the denominator. Are we there? So we'll collect like terms. So collecting like terms here, what we'll simply be having here will now be 0.5 V1, right, minus 0.5 V2. I'll now bring 0.33 V2 from the right hand side to the left hand side become negative. So we have minus 0.33 V2 minus 0.5 V3. Then I'll bring 0.33 V3 from the right hand side to the left hand side become what? Negative. So we have negative 0.33 V3. Then I'll now move the positive 5 to the right hand side, will now become negative. Is that okay now? So if I move further, this will now give me 0.5 V1 minus 0.5 V2 minus 0.33 V2 will give you 0.8 V2 minus 0.5 V3 minus 0.33 V3 will give you 0.83 V3 equals to minus 5. So I'm using V2 because they are all like terms and V3 also. I hope you understand that. Now we'll term that equation 9. Now we've gotten two equations. Equation 9 and also equation 4. Look at it closely. You see that there's something odd about these two equations. I cannot easily use them to work simultaneously, right? So I need to make them conform. They should have something in common. So what is differentiating both of them is V3. I have V3 in equation 9, but I don't have V3 in what? In equation 4. So I need to eradicate that V3. That is when I will now consider the supernode C, right? So when you see the supernode will now be the one helping here. That's why we call it is super, because it's trying to help out to eradicate V3 from that equation here. So let's go and consider that supernode C. Now from the supernode C, you can see, right? Now it will be, we are moving towards the right. Why? Because current flows from a lower potential to a higher potential. Current move from the negative terminal to the positive terminal, right? So if we are moving towards from supernode C to D, it will be from where the voltage from where the current is flowing from is V2, right? Plus the voltage in between them is 5, right? Minus the voltage to where we are moving to, which is V3. So V2 plus 5 minus what? Minus V3. Is that taken now? So that is what we have here. And it can be vice versa. If the polarity was reversed, right, it will be V2 minus 5, right, minus V3. Are we together? So let's not confuse ourselves about that. So equals to 0. So if I now make my V3 sort of the formula, that means I'll move negative V3 to the right hand side. We'll now be having V3, positive V3 equals to V2 plus what? 5. That will term that my equation 10. Now substitute V3 equals to V2 plus 5 into equation 9. So we'll now be having 0.5 V1 minus 0.83 V2 minus 0.83 V3, but I will not write V3 now, I will now write the value of V3, which is what? V2 plus 5 equals to negative 5, right? Now, if I simplify further, 0.5 V1 minus 0.83 V2 minus 0.83 times V2 give you minus 0.83 V2 minus 0.83 times plus 5 will give you minus 4.15 equals to minus 5. So if I move further again, I'll be having 0.5 V1, then minus 0.8 V3 minus 0.8 V3 will give you minus 1.66, minus 0.83 V2 minus 0.83 V2 will give you minus 1.66 V2, right? Equals to minus 5, I'll take minus 4.15 to the right hand side, it will become plus 4.15. So 0.5 V1 minus 1.66 V2 is equals to what? Minus 0.85. I'll term that my equation 11, right? So combining equation 4 and 11 now, since they are now conforming, from equation 4, I have 10 equals to 1.5 V1 minus 0.5 V2. That's my equation 4. From equation 11, I have minus 0.85 equals to 0.5 V1 minus 1.66 V2. That is my equation 11. Now we are going to solve this simultaneously using elimination method. And you know one of the rules of elimination method, you need to make any of the coefficient of the variable, either V1 or V2, to be the same. So if I'm considering V1, that means coefficient of V1 in equation 1 must be equal to coefficient of V1 in equation 2. You remember all this. So what I'll do is, to make this happen, I'll use the coefficient of V1 in equation 11, which is 0.5, to multiply equation 4, and I'll use the coefficient of V1 in equation 4, which is 1.5, to multiply equation 11. So if I'm doing that, I'll be having this to be, if you multiply 0.5 times 10, I'll have 5. If you multiply 0.5 times 1.5 V1, I'll have 0.75 V1. If you multiply 0.5 times 0.5, I'll have 0.25 V2. I'll term that equation 12. Similarly, if you multiply 1.5, which is coefficient of V1 in equation 4, by 0.85, I will have 1.28. Multiply 1.5 by 0.5, I will have 0.75 V1. If you multiply 1.66 by 1.5, I'll have 2.49 V2. Is that okay? I'll term that my equation 13. Now, since you see now both quotient of V1 in equation 1, in equation 12 and equation 13 is now the same, which is 0.75. Now, since they are the same, they are positive. So what I have to do, I have to subtract both of them in order to equate one of the equation. So what does that mean? It means that before I should add them, I should multiply equation 3 by what? By minus what? Minus 1. So what does that mean? So if you multiply equation 13 by minus 1, so you multiply equation 13 by minus 1, you'll be having plus 1.28 equals to minus 0.75 V1 minus times minus give you plus 2.49 V2. So I've multiplied through by negative. So I've changed their sign. Now I cannot add. So 5 plus 1.28 give you 6.26. 0.75 minus 0.75 will give you 0. Minus 0.25 plus 2.49 will give you 2.24 V2. Is that okay now? So now make V2, sorry, the formula, my V2 will now be equals to 6.28 divided by 2.24. So my V2 will now be giving me 2.80 volts altogether. Now substitute V2 equals to 2.80 into equation 4. So my equation 4 is 10 equals to 1.5 V1 minus 0.5 V2, right? So when you put your value, my 10 will now be equals to 1.5 V1 minus 0.5 V2. I will not write V2 now, I'll write the value of V2, which is 2.80. So 10 will now be equals to 1.5 V1 minus 0.5 times 2.80 is 1.4. So if I collect like terms, I'll move minus 1.4 to the left hand side of the equal sign. So I'll be having 10 plus 1.4 equals to 1.5 V1. So 10 plus 1.4 is 11.4 equals to 1.5 V1. So V1 will now give me 11.4 divided by 1.5. So we're having this to be 7.6 volts. So we've gotten V1. So this is the value of V1 and this is the value of V2. Substitute your V2 equals to 2.80 into equation 10, right? So we know equation 10 is V3 equals to V2 plus 5. So V3 will now be equals to V2. Instead of putting the value of V2, you put 2.80, right? Plus 5. So my V3 will now be equals to 7.80 volts. So therefore, the value of my V1 is 7.6 volts. Value of my V2 is 2.80 volts. Value of my V3 is what? 7.80 volts. So substituting into equation 2, 3, 6, 7, and 8. So for equation 2, we have I1 equals to V1 and the value of V1 is 7.6. So I1 is what? 7.6 ampere. Then equation 3, we have the value of I2 to be equals to what? V1 minus V2 all over 2. So if we insert the 2 value to be 7.6 minus 2.80 divided by 2, and that will give me 4.8 all over 2, and that will give me 2.4 ampere. I3 is giving, if you substitute into equation 6, which is I3 is equals to V2 all over 3, and value of V2 is 2.80 all over 3, and that will be equals to 0.93 ampere. I4, that is the next equation, is I4, which is equals to V3 over 3, and the value of V3 is 7.80 divided by 3 will give us 2.6 ampere. And for the next equation, the equation 7, is I5, and I5 is equals to what? 10 minus V3 all over 2. And that will be equals to what? 10 minus the value of V3 is 7.80 divided by what? Divided by 3. And that will give us what? 0.73 ampere. So we have successfully calculated for the branch currents and the mesh currents, which I have shown you on the screen. So my I1, I2, I3, I4, and I5 are 7.6 ampere, 2.4 ampere, 0.93 ampere, 2.6 ampere, and 0.73 ampere respectively. So if you have found this video helpful, please don't forget to like the video, subscribe to the channel, and also share the video. Thanks for watching.